Hello. Take your seat, please. The next plenary talk will begin. Take your seat, please. So the next plenary talk will begin. Professor Carl Pomerance will speak. The title is written there. I think it is not necessary to introduce Professor Pomerance. He is a well-known scientist working on number theory. And please.
Thank you very much. It is a great pleasure to be speaking here, a very high honor, and I thank the organizers for inviting me. I also want to thank them for this wonderful Congress. What better way to honor Paul Erdős than to have not only many of his old friends here, but many people who he would certainly become friends with if he were to meet them now. My talk is, the slides for this talk are available on my web page, and the talk itself is based on a longer survey article in the proceedings. Okay, hopefully I can be audible. The article in the proceedings on which this talk is based is jointly written with Paul Pollack. Now, the beginning of my talk is sort of historical and perhaps not completely serious. You might detect that I'm being a little defensive about the subject, and you'll see why. Because in fact, elementary number theory, as beautiful as it is, has been attacked. And we will see what I'm talking about. Let's begin at the beginning with Pythagoras. So 2,500 years ago, he defined what might be the very first ever mathematical function. I don't know of an earlier example. Given a positive integer n, he says to add up the divisors of n that are smaller than n itself. So some examples for 10, 11, and 12. You can see them written here. S of 10 is 8, S of 11 is 1, just like S of any prime would be 1, and S of 12 is 16. In more modern notation, we include n itself in the sum of divisors because we have now sigma of n, and sigma of n is a multiplicative function, so in some sense it's nicer than S of n, but of course if you know one of these, you know the other. So Pythagoras, when considering this, not only perhaps defined the very first function of all time, he also perhaps had the very first dynamical system of all time, because he suggested that one iterate the function s. And so, for example, he noticed that 6 is a fixed point under this iteration. S of 6 equals 6. We say these fixed points are perfect numbers. And here's a 2-cycle, also due to Pythagoras. So if you add up the proper divisors of 220, you get 284. And if you add up the proper divisors of 284, you get 220. I don't know if it's recorded that he discovered other cycles. Of course, a few hundred years later, Euclid found some more perfect numbers. Pairs like 220 and 284, these 2 cycles, have been called amicable pairs, and the numbers themselves have been called amicable numbers. This is a colorful thing in the history of number theory, and the question is, just because Pythagoras did it, and just because it's colorful, does it mean that we should be studying it? So, Enrico Bombieri is a great mathematician, and I have a lot of admiration for him and his work. He wrote in an article in 1976, this was an article about Hilbert problems, maybe it was 75th anniversary of Hilbert's famous problem list, and so the issue was problems, and he wrote the following in the introduction to his article. There are very many old problems in arithmetic whose interest is practically nil. For example, the existence of odd perfect numbers, problems about the iteration of numerical functions, the existence of infinitely many Fermat primes, 2 to the 2 to the n plus 1, etc. I remember Paul Erdős calling this quote to my attention, saying, what do you think of this? And Erdős, as you know, often didn't get angry, but he was not happy with this, with Bombieri saying this. Now, in some sense, I think there's truth in what Bombieri wrote, but I'd like to qualify that truth. Because not every problem is good. I think Paul Erdős knew this. He knew that's why we revere his problems, because so often his problems were good. It's not easy to come up with good problem after good problem after good problem. Sir Fred Hoyle was not a mathematician, but an astronomer. And he wrote in a popular astronomy book in 1962 that there were two difficult astronomical problems faced by ancient people. And one of these problems was a good problem, and one of them was not so good. Here are the two problems. The good problem was, why do the planets change their positions in the constellations among the stars? How is this happening? How can you predict where the planets will be next? This was a very difficult problem, and trying to solve it was, well, it was so difficult that you just didn't say, okay, let me think about it. Okay, I understand. It didn't happen that way. It happened over a long period of time that we got to understand how this happened. And it helped us develop science and mathematics. It was a great problem for us. The not so good problem. Why is it that the sun and the moon are the same apparent size? That problem didn't lead anywhere. So you can ask the question about these ancient topics, such as perfect numbers and amicable numbers and so on, and ask, are these good problems or are they not so good? Okay, so I'd like to give a small amount of evidence on this slide and the next that they are good problems. First of all, studying them they were of interest to lots of people, and studying them helped us develop all of elementary number theory, and from elementary number theory we developed the rest of number theory, and also you can argue that from elementary number theory came algebra. We'll see in this talk that probabilistic number theory owes its inspiration to some of these problems. The computational challenges posed, say, by perfect numbers, by finding examples of even perfect numbers or testing primality of numbers that are 1 less than a power of 2. These helped develop algorithmic number theory, which has become a very important subject. Diophantine equations. For example, the Catalan equation, which asks, are 8 and 9 the only consecutive non-trivial powers? Exponential Diophantine equations, such as that one, bear a resemblance to issues involved with odd perfect numbers. So with these connections, and you can argue that perhaps these ancient problems were good problems in the sense of Hoyle. But we should try to think of things from Bombieri's perspective as well, and not just immediately dismiss him. And one of the reasons why maybe elementary number theorists are on the defensive is because of this maybe too colorful history surrounding them. So let me explain a little bit about that. These concepts were, I think maybe you know that before there was number theory, there was a subject called numerology. So let's see how these fit in those days. So for example, St. Augustine wrote about perfect numbers. This is very interesting to me. 6 is a perfect number in itself, and not because God created all things in 6 days. Rather, the converse is true. God created all things in 6 days because the number is perfect. So now you know the rest of the story, right? Okay. So here we have a Talmudic scholar talking about amicable numbers. In Genesis, it's related that Jacob gave his brother Esau a lavish gift so as to win his friendship. The gift included 220 goats and 220 sheep. So Abraham Azalai wrote about 500 years ago, our ancestor Jacob prepared his present in a wise way. This number 220 is a hidden secret, being one of a pair of numbers such that the parts of it are equal to the other one, 284, and conversely. And Jacob had this in mind. This has been tried by the ancients in securing the love of kings and dignitaries. The Islamic scholar Ibn Khaldun wrote 600 years ago in Muqaddimah something very similar. Persons who have concerned themselves with talismans affirm that the amicable numbers 220 and 284 have an influence to establish a union or close friendship between two individuals. And it gets wilder. So in Aim of the Wise, al-Majriti wrote about a millennium ago. It is about the erotic effect of amicable numbers, and that this has been put to the test by giving anyone the smaller number 220 to eat, and himself eating the larger number 284. Now, I'm not sure what they're serving for lunch today, but I claim this was a very early application of number theory, far predating public key cryptography. Our last visit to the ancients, Nicomachus, who lived 1900 years ago. He defined abundant numbers and deficient numbers. And when you see some of these films of Erdős lecturing, Erdős is defining an abundant number. These were first defined 1900 years ago, but they were defined in a very colorful way, where he goes on and on talking about the personalities of these numbers. So, in fact, I call it his Goldilocks theory. So, again, in the definition, what is an abundant number and a deficient number? Remember the function S of n. S of n is the sum of the proper divisors of n. And if it's greater than n, then n is abundant. And if it's less than n, n is deficient. And if it's equal to n, then n is perfect. So Nicomachus wrote, in the case of too much, namely abundant numbers, is produced excess, superfluity, exaggerations, and abuse. In the case of too little is produced wanting, defaults, privations, and insufficiencies. And in the case of those that are found between the too much and the too little, that is inequality, is produced virtue, just measure, propriety, beauty, and things of that sort, of which the most exemplary form is that type of number, which is called perfect. So this is what elementary number theory has to work with. This is where we start from, and you can see why it's, we're supposed to be serious scientists. Why, how can you say that this is a serious subject with such a background as this? Now, there is a way out of this, and the way out of it is to think statistically. And by statistically, I don't mean like a biologist necessarily would think about tests for the validity of some biological theory or some medicine or something like that. I'm thinking just more simply of just counting. In 1929, in a survey article he wrote on number theory, Eric Bessel-Hagen raised the issue about the asymptotic density of the abundant numbers. So for example, it's pretty easy to see that every number that larger than 6, that's a multiple of 6, is abundant. So the lower density of the abundant numbers is at least 1/6. And so the question is there a positive proportion of numbers that are abundant? So in his 1933 doctoral thesis, Berendt proved that the lower density is larger than 0.241, and the upper density of the abundant numbers is smaller than 0.314. And later that year, Harold Davenport actually answered Bessel-Hagen's question and proved that the density exists. In fact, Davenport proved a much stronger theorem. So consider the function d sub sigma of u. D sub sigma of u is the density of integers n which satisfy the inequality sigma n divided by n less than or equal to u. So if u is equal to 2, then these numbers n include the perfect numbers and also the deficient numbers. And so the complement of this set when u equals 2 is the set of abundant numbers. And so Davenport proved that this density exists, and in fact this is a continuous function of the letter u. So as I said, the abundant numbers have the density 1 minus d sub sigma of 2. And this number is not so easy to compute. Delagliese had this number to 3 decimal places, and recently Mitz Kobayashi found this to 4 decimal places. So the density of the abundant numbers starts with 0.2476, and we don't know what the next decimal place is because it's a hard function to compute. Now, Davenport's proof of this very nice theorem was analytic and technical, and also did not really stand on its own. It was based on a proof of a similar result from 5 years earlier by I.J. Schoenberg. And Schoenberg's similar result dealt with a similar function. Instead of looking at the ratio sigma n over n, Schoenberg looked at the ratio n divided by phi of n. Here, phi is Euler's function. And this ratio n divided by phi of n is a very similar to the ratio sigma n divided by n. So in his early 20s, Erdős learned of these things, became very interested in the subject, and he began looking for a more elementary way of studying it, of finding these densities, and also looking for, okay, we have a theorem for n over phi of n, we have a theorem for sigma n over n, for which multiplicative functions do we have a theorem? So this culminated in 1939 with the Erdős-Wintner theorem. Erdős developed over the intervening years a number of partial results, and then Wintner helped with the last step. And here's a statement of the Erdős-Wintner theorem. So we start with a multiplicative arithmetic function f. So you should think of f being sigma of n, the sum of the divisors of n, or f being phi of n, Euler's phi function, and or something like that. And now we look at its logarithm. So the logarithm of multiplicative function is an additive function. So here we have this g of n. It's now a real valued additive function. And we look at 3 different series. The series are all over primes, but the primes are restricted in the 3 series. In the first series, the primes have g of p in absolute value being greater than 1. And then we're just summing the reciprocal of those primes p. In the second series and third series, g of p is in the complementary set where of absolute value less than or equal to 1. And in those two series, we sum g of p squared over p and g of p over p. And so a necessary and sufficient condition for f, the function f, to have a limiting distribution is that these three series converge. A beautiful theorem. And furthermore, there's a simple criterion for the distribution function, this d sub sigma of u of the Davenport, for example, to be a continuous function. And the condition is that a fourth series should diverge, the series of 1 over p, where g of p is not 0. If it's continuous, there's still further issues to decide, for example, whether it's absolutely continuous or purely singular, but I won't get into that. Let's look at an example. So f of n is sigma n over n. This is a multiplicative function. Its value at a prime p is 1 plus 1 over p. And so the function g of p that we saw in the previous slide is just the log of 1 plus 1 over p. Now we know from Taylor's theorem, for example, that the log of 1 plus 1 over p is approximately 1 over p. So let's go back and look at those three series. If g of p were just 1 over p, then it wouldn't be bigger than 1. So the first series would be at worst a finite series, so certainly it would converge. So the second series involve essentially all the primes. But the g of p is 1 over p, so this is the series 1 over p cubed, and this is the series 1 over p squared. They both converge. So the three series all converge, and we have a limiting distribution. Furthermore, this fourth series, g of p is never 0, so this series diverges, and so it's continuous. And we have the Davenport theorem. So I think this, going back, Nicomachus had this very colorful way of describing abundant numbers and so on. I'm happy that he brought it to our attention. Just look, now we have this beautiful theorem that led to exactly this. Let's look at, now that we're on the subject of distribution functions, let's take another common function. This is the function omega of n. Omega of n is not multiplicative. Omega of n is defined as the number of different primes that divide n. It's an additive function. So it's sort of already playing the role of the logarithm of a multiplicative function. In other words, I could have started with the function 2 to the omega of p. That's a multiplicative function, and then its logarithm essentially is omega of n. So let's look at the three series for this function omega of n. So omega of p is always 1. So the second and third series contain all the primes. The absolute value of g of p is less than or equal to 1. Well, it's equal to 1 for omega of p. And so the series diverge. The series would be 1 squared over p over all primes p, and 1 over p for all primes p. Those are divergent series. So the Erdős-Wintner theorem fails for omega of n. So it doesn't have a limiting distribution. Well, what can we say about omega of n? Well, the answer to this is connected to some other talks at the same meeting. There's a threshold function involved with omega of n. This was determined some years earlier by Hardy and Ramanujan. They proved that omega of n divided by log n, that tends to 1 on a set of asymptotic density 1. In other words, if you looked at the inequality omega of n less than 1 minus epsilon times log n, that set of n has asymptotic density 0. And if you looked at the set of n where omega of n is greater than 1 plus epsilon times log n, that set of n has asymptotic density 0. For almost all n's, omega n is approximately log n. All the action is happening there. So what we should be doing is looking at the difference, trying to look at the difference between omega n and log n. This thought culminated in another fantastically beautiful theorem, the Erdős-Katz theorem. And here's the complete statement of it. So here we have a certain set of integers, and the variable that's in this set is the letter u, that you can see on the right side of the inequality. So the letter u is just a real variable. It can be any number, positive or negative. And we're looking at the set of integers n such that omega n minus log n is less than or equal to u times the square root of log n. In other words, the measuring stick here is the square root of log n. So this set has an asymptotic density, and it's given by this formula, 1 over square root of 2 pi, integral minus infinity to u e to the minus t squared over 2 dt. You'll recognize this as the Gaussian normal distribution. The derivative of this function of u is the bell curve. Surely this has to be one of the most beautiful theorems in number theory, if not all of mathematics, to connect the bell curve with the number of prime factors of an integer. As we know, Paul Erdős died too soon. He died in 1996 in the fall. In January of the next year, at the joint math meetings in the United States, Ron Graham organized an impromptu session to remember Paul Erdős, and he asked me to say a few words at this session on Erdős's work in number theory. So, of course, I had to explain the Erdős-Katz theorem in my talk. And I was looking around for a way to make this more colorful. I don't see why I needed to do that, because the theorem stands on its own already as being incredibly beautiful, but for some reason I tried to embellish it. And so this is what I did. I had a slide where I quoted Einstein. This is a correct quote of Einstein. Einstein was unhappy with the theory of quantum mechanics, and he wrote, God does not play dice with the universe. And then I said, I would like to think that Erdős and Katz replied, maybe so, but something's going on with the primes. Now, I'd like to emphasize now to this group that I made that up. Erdős and Katz did not say this. This was a joke. However, there was a reporter in the room, and he didn't understand so much of what was happening in the session, but he understood this, except he didn't get the joke part. He thought maybe this was really said. And so it was reported in the newspaper the next day that, well, actually, it was even misquoted. It said, Erdős said it, Katz got left out. And this has sort of taken on a life of its own, this false quote of Erdős. And in fact, if you go on the web and look at this book by Wells called Prime Numbers, the Most Mysterious Figures in Math, and look on the dust jacket of the book, you can see some paraphrase of this quote that never existed. It's sort of frightening how you can change history just like that, isn't it? Now, there's some background on the Erdős-Katz theorem, because it just didn't fall from the sky. It didn't arise spontaneously in 1939. I had mentioned that Hardy and Ramanujan had shown that normally omega of n is about log n. The proof of Hardy and Ramanujan was a little bit technical, perhaps not made in heaven, not from the book. And in 1934, Paul Turan found the book proof of the Hardy-Ramanujan theorem. And basically what he did is in retrospect, he computed the first moment of the average value of omega, and he computed the second moment. And however, he didn't put it in those terms. And in fact, in this book, Probabilistic Number Theory, written by Peter Elliott. Elliott quotes HUN-REN from 1976, and HUN-REN says, I did not know what Chebyshev's inequality was in a fortiori the central limit theorem. Erdős, to my best knowledge, was at that time not aware too. It was Mark Katz who wrote to me a few years later that he discovered when reading my proof in JLMS that this is basically probability, and so his interest turned to the subject. And Elliott also quotes Mark Katz in the same, around the same place in the book, and Katz writes, if I remember correctly, I first stated as a conjecture the theorem on the normal distribution of the prime divisors during a lecture in Princeton in March 1939. Fortunately for me, and possibly for mathematics, Erdős was in the audience, and he immediately perked up. Before the lecture was over, he had completed the proof, which I could not have done, not having been versed in the number theoretic methods, especially those related to the sieve. So that's the background of the wonderful Erdős-Katz theorem. Let's return to the subject that I began with at the beginning of this talk, namely amicable numbers. So we saw that 220 and 284 are amicable numbers. In fact, they're the first pair. They were discovered by Pythagoras. The sum of the proper divisors of 220 is 284, and vice versa. People have found examples through the ages. Tabit ibn Qurra found a formula that gave a few. Euler found a few. Now with computers, we found quite a few. We're up to 12 million pairs, approximately. But no one has ever proved that there are infinitely many. How do you think Erdős would approach this problem of amicable numbers? Why count them? Now, as I just said, we have 12 million pairs. I'm sure Erdős, if he wanted to, could count 12 million pairs, but he would wanted to do up to x and see how the number of amicable numbers, what can you say about the number of amicable numbers up to x? So let's let a of x be that count. We don't have a good lower bound. We don't know that a of x tends to infinity, but what about an upper bound? Can we prove that a of x is a small function of x? So perfect numbers are closely related to amicable numbers. They're the fixed points for the function s. And an immediate corollary of Davenport's theorem on the density of sigma n over n being less than or equal to u, it follows immediately from the continuity of that function that the perfect numbers have asymptotic density 0, because they are the n's where sigma n over n is between 2 minus epsilon and 2 plus epsilon. All the perfect numbers are contained in that set, and as epsilon tends to 0, the density of n's that satisfy that inequality tends to 0 by continuity. But we know stronger results than just density 0, and Erdős was, of course, had a role in this. His result was less than x to the 1/2 minus c for some c positive. The best result that we have is due to Hornfeck and Versing, who proved that the number of perfect numbers up to x is less than or equal to x to the little o of 1. But amicable numbers, we only know about 46 or so perfect numbers. We know 12 million amicable pairs. Maybe the amicable number function count is much larger. So Erdős in 1955 was the first to show that a of x is little o of x. In other words, the amicable numbers have density 0. And his insight on how to prove this was the following. He put the amicable numbers into a larger set. The larger set were, well, the smaller member of an amicable pair, its sum of divisors is the other number, so the smaller member of an amicable pair is abundant. Yet s of that smaller number is the larger member of the pair, and that number is deficient. So the larger set to consider is those n that are abundant, such that s of n is deficient. And just that property is enough to show density 0. In other words, I'm defining here on this slide a new function for convenience. H of n is sigma n divided by n. And so the definition of being abundant is that h of n should be bigger than 2, and definition of being deficient is that h of n is smaller than 2. So we're looking at the n's up to x for which h of n is greater than 2 and h of s of n is smaller than 2. And we'd like to show that that set of numbers n has asymptotic density 0. So to prove this, Erdős did it as follows. First of all, to say that h of n is greater than 2, the distribution function is continuous. So except for a small exceptional set, we can say we can improve the inequality greater than 2 and say that it's actually bounded above 2, except for a small exceptional set. So we replace h of n greater than 2 with h of n greater than 2 plus delta. Now the function h of n, which is sigma n over n, can be rewritten as the sum of reciprocals of the divisors of n. Let's define a truncated version of that, h sub y of n. So now we're summing the reciprocals of those divisors of n that are less than or equal to y. Now, small numbers have large reciprocals and big numbers have small reciprocals. So you'd think that if y has some size to it and we just sum the reciprocals of the divisors of n up to y, that should be pretty close to the full sum. And so by an averaging argument, he shows that that's true. And in fact, if you do that, we can assume that this truncated version of h of n is, in fact, greater than 2. Since h of n was greater than 2 plus delta, we have a little bit to play with. And so now we have this h sub y of n greater than 2. So this was all easy stuff for him. But now came his brilliant coup in solving this problem. Let capital M be the least common multiple of all the integers up to y. So y is just some big finite number, and so m is some even bigger finite number, but it's finite. And the claim is that almost all numbers n except for a set of density 0 are divisible by a prime p to exactly the first power, such that p is in a particular residue class mod m. The residue class is minus 1. So p plus 1 is divisible by m. And this uses the proof of this is actually not so hard. It uses Dirichlet's theorem on primes in a residue class. The sum of the reciprocals of primes p that are in this residue class is infinite, and so therefore the density of integers that are free of primes from that residue class have density 0. But this does it because if n is divisible by p to the first power and p plus 1 is divisible by m, that means that p plus 1 is a divisor of sigma of n, and therefore m is a divisor of sigma of n. And so therefore, if we look at s of n, we see that, okay, in the equation s of n equals sigma n minus n, all the integers up to y divide sigma of n. And so therefore, s of n, that number, and n, that number, they have the same divisors up to y. And so therefore, the sum of reciprocals of divisors of s of n is trivially greater than or equal to the truncated sum of divisors of s of n up to y. But we just argued that that's exactly the same as the truncated sum of reciprocals of divisors of n up to y. And we already argued earlier that that's greater than 2. And this contradicts that h of s of n was supposed to be smaller than 2. And so this shows that the set of n's that we're considering are all in these small exceptional sets that we were throwing away. And it proves that the amicable numbers have asymptotic density 0. So I wanted to give one example of an Erdős proof in this subject, and I like this example. I later gave another proof of amicable numbers having density 0 using a much earlier paper of Erdős written in 1935 on primitive abundant numbers. And still another paper, I used another method, and I showed that the reciprocal sum of the amicable numbers is finite. So I'd like to change topics slightly now and talk a little bit about computational number theory. Erdős, as has been said by others here, was not working directly in algorithmic issues, but he did have his influence. In a paper that I wrote with Erdős and also Rod Canfield in 1983, we, as a lemma in this paper, we worked out, in fact, this lemma was not the main point of the paper, but it was useful for what was the main point. We worked out the distribution of smooth or friable numbers. These are numbers, all of whose prime factors are small. We worked out their distribution to enough accuracy to give guidance to algorithms that depended upon smooth numbers in their analysis. So, for example, factorization algorithms and discrete logarithm algorithms. So this became sort of the go-to paper for quoting results on smooth numbers. Now, even though this is a well-quoted paper, it doesn't even make Erdős's top 10 quoted papers, but it's close. It's Erdős's 13th most cited paper on MathSciNet. Of course, this is a little bit inaccurate because MathSciNet is sort of prejudiced against old papers. It's only looking at more recent quotations, citations. It's, for Canfield and myself, it's our #1 cited paper. Here's something else, some other connection of Erdős to computational number theory. Everybody knows Fermat's little theorem in elementary number theory. Fermat says that if p is a prime and a is any integer, then a to the p is congruent to a mod p. Now, this is a very easy congruence to numerically check. And the question is, can you turn it around? If a to the p is congruent to a mod p, must p be prime? So say a counterexample to the converse is a pseudo-prime. So a composite number n with a to the n congruent to a mod n is called a base A pseudo-prime. It'd be nice if they didn't exist, but they do exist. And here's an example with a equal 2. That's easy to verify even mentally if you think about it the right way. 2 to the 341 is congruent to 2 mod 341, yet 341 is not a prime number. That's 11 times 31. So pseudoprimes exist, and so pseudoprimes together with the primes satisfy a to the n congruent to a mod n. Which are more common, primes or pseudoprimes? Erdős was the first to show that for every fixed base a, the pseudoprimes are very rare in comparison to the primes. And due to this, due to Erdős's theorem that shows that the composite solutions to Fermat's little theorem are rare compared to primes, this suggests a primality test. It's never been called this. We could call it the Erdős primality test. Here's how it goes. You want to find a large random prime number. Say you want to build the RSA crypto system or something like that. Choose a large random number n, and then check numerically to see if 2 to the n is congruent to 2 mod n. If it doesn't work, if that congruence fails, then choose again. Choose another large random number n. Eventually, you should get one, a number n, such that 2 to the n is congruent to 2 mod n. Accept it. Believe it. Say that n is prime. And, well, you could be wrong. It could be that it's composite. It could be that it's a pseudoprime. But the odds of it being composite are actually very small. And so this compelling test, which is extraordinarily simple, would work in practice. You would not lose money for your company if you set up your RSA crypto system in such a way. Erdős was also very interested in Carmichael numbers. So these are numbers like 561 that are not only pseudoprimes to the base 2, but also pseudoprimes to the base 3. In fact, pseudoprimes to every base. In 1956, Erdős has an article about Carmichael numbers, about their distribution, where he got an upper bound, which essentially is the best upper bound that we have. It says that C of x is less than, C of x, the number of Carmichael numbers up to x, is less than or equal to x to the 1 minus epsilon, where the epsilon tends to 0 slowly as x tends to infinity. That epsilon is constant times triple log over double log. Now, he also gave a heuristic argument based upon a seminal paper of his from 1935 that this was essentially a best possible result. Now, the shape of this is x to the 1 minus epsilon, and if this is best possible, he's saying that C of x is greater than or equal to x to the 1 minus epsilon for all sufficiently large x. In 1993, in a paper that we dedicated to Erdős on his 80th birthday, Alfred Granville and myself proved that there are infinitely many Carmichael numbers. We got the lower bound x to the 2/7, and we used the Elliott-Halberstam conjecture to prove the Erdős conjecture that it's greater than x to the 1 minus epsilon. The Elliott-Halberstam conjecture is just an assertion about the regularity of distribution and residue classes of prime numbers. Now, I mentioned this seminal paper of 1935, which was important for Erdős's thinking on Carmichael numbers. This was a paper he wrote in the Quarterly Journal of Math in the Oxford series. Here's how the top of the paper, and I'd like to call your attention to the date the paper was received at the journal, 13 November 1934. So we know when Erdős was born. When he sent this paper to the journal, he was 21 years old. And this paper is, to my way of thinking, one of his most important papers. The title is On the Normal Number of Prime Factors of p minus 1 and Some Related Problems Concerning Euler's phi function. I mentioned before that Hardy and Ramanujan showed that a number n has normally about log n prime factors, but a prime p, it's not normal. It only has one prime factor. Okay, subtract 1 from p. How many prime factors does p minus 1 have? And Erdős showed that p minus 1 is normal. He showed that it has about log p prime factors for most primes p. He used Brun's sieve to do this. It's one of the things of which Erdős is very famous, showing the power of sieve methods in elementary number theory. In this same paper, he used this to attack a problem of Pillai. Pillai asked how many numbers up to x are values of Euler's function. You can see instantly, since Euler's function takes a prime p to p minus 1, that there are at least about x over log x Euler values up to x. That's a lower bound. What about an upper bound? And Erdős showed that the x over log x was also correct as an upper bound. He got x over log x to the 1 plus little o of 1. He also got this astounding theorem that said there are some values of Euler's function that are extraordinarily popular. He proved that there's a positive constant c and infinitely many integers capital N, such that there are more than capital N to the c solutions to phi of n equal capital N. He gave a heuristic argument that the c should be arbitrarily close to 1, but he only proved that it was positive. And it was this circle of thinking that led to his thinking on Carmichael numbers and also to the proof of the infinitude of Carmichael numbers. The current record for C, due to Baker and Harman, is about 0.7. On the issue of number of Euler values up to x, a number of people have looked at this problem trying to get better results, including Erdős himself with Richard Hall. Also, I worked on this with Helmut Meyer. And the champion result is due to Kevin Ford. And here it is. It has lots of iterated logs. So log sub 4, for example, refers to log x. I'm sure if Erdős were here writing, he'd write out all those logs, but it was fun for him to do so. Like Fermat, it would be too big for the margin if I wrote it out in all its glory. So I'm using the subscripts. The numbers C1, C2, C3 are explicit constants. And this is the actual order of magnitude of the count of Euler functions up to x. We still don't have an asymptotic formula. Now, the sum of divisors functions, sigma of n, is very similar, and in some sense they're twins. Erdős asked in the late 50s if the ranges of phi and sigma had an infinite intersection, and it's easy to see that the answer to this is yes, if there are infinitely many twin primes. That's not yet been proved, although maybe Jean comes close. If p and p plus 2 are both prime, then phi of p plus 2 is the same as sigma of p. It's also true if there are infinitely many Mersenne primes, primes that are 1 less than a power of 2, as you can see on the slide. At one point, I proved it was also true if the extended Riemann hypothesis held, although I didn't write that up. But at this point, I started hoping that I could disprove the conjecture. Because if I could disprove the conjecture, then I would also have a corollary that the extended Riemann hypothesis is false. There are only finitely many Mersenne primes, and there are not infinitely many twin primes, which would be some nice corollaries. Unfortunately, Erdős's conjecture is true, and this was proved recently by Ford, Luca, and myself. I'd like to close this talk with one last problem going back to Euclid. Euclid perhaps was the first person to think statistically because he proved that there were infinitely many primes. Here's a detail of a painting of Raphael from 1510 of Euclid teaching. I really like this picture. I feel some sort of kinship of with these, with Euclid and ancient mathematicians. They're doing the same kind of thing that we do, teaching. 2,000 years passed, and Euler made another point of progress. The sum of reciprocals of primes up to x tends to infinity like log x. Approximately 50 years later, maybe it was 60, Gauss and Legendre came up with a conjecture for the count of primes up to x, that it should be asymptotically x over log x. In the mid-19th century, 1850s, 50 years later, Chebyshev and Riemann had results. Chebyshev got an approximate formula for pi of x. Riemann laid out a proof, laid out a plan to prove the conjecture. 1890s, about 50 years later, Hadamard and Delavalle-Poussin actually proved the prime number theorem. About 50 years later, Erdős and Selberg gave an elementary proof. It's now a little beyond 50 years later. I think we're waiting for the next installment in this. Somebody have the Riemann hypothesis, perhaps? I would like to think that beyond the prime number theorem, Erdős was searching too for the amicable number theorem, the perfect number theorem, and so on. In all of these problems and results, we can see echoes of the past at the dawn of number theory and mathematics. We might never solve these ancient problems completely, but thinking about them statistically has made all the difference, and leading the way was Paul Erdős. Köszönöm. Thank you.
Thank you very much. This very interesting talk. Are there any questions, please? Yes, please.
Was there any reference in the Erdős series theory to mention
Connections to Kolmogorov? I don't know of any. I don't know of any connections, but that would be interesting.
Any other question, please? If not, then thanks again. Very nice talk. Would you like to speak something?
And let me have my usual dull announcements, but before you leave, please stay for a while because Ron Graham is going to have a more interesting announcements after my dull announcements. So, the same story which I gave you yesterday and before yesterday, the staff of the Academy is happy to serve you a very nice lunch here down in the restaurant. Still, they didn't reach the capacity. If you want to dine in an environment like this magnificent room is for a relatively good price, just go down, they can serve you. Boat tickets, we are nearing the capacity of the boat, and I know some of you are not very happy about the strict rules to enter this building, but I can just repeat that for your own safety and security, we have to enforce that. Now, be sure that the boat is going to be even more secure and safe. Unfortunately, they have a limit, so for them it's even more important not to allow more people on board than they are allowed to. So if you really think, if you still think to come to the boat and you have not picked up your ticket, please don't forget to do it today during the lunch break. This is your last chance. We have to close that option after that. Okay, thank you. Now, the organizers, other organizers asked me to ask the poster session exhibitors to remove their posters from the stands today, those who have them, because from next morning, tomorrow morning, we are going to have the new poster sessions. And finally, I would like to tell again that the books exhibition now is on full gear. Everybody arrived, all the books are there. And by now, I hope even Wim Pham arrived from Paris. He's the illustrator of the tale book about Uncle Paul. And as she wrote me, she's willing to draw a picture of you. The lower your Erdős number, the nicer the picture is going to be. So you can just... This is what she told. So you can just visit her stand in the books exhibition room and have a picture of you. And now Ron is going to tell you something.
Yes, a very quick new discovery on the Erdős lap number graph that László Lovász mentioned. And here's the first picture. This is part of the proceedings of a number theory meeting and conference in 1969. And you'll probably notice here, there's a Polybachi with someone in his lap. And so she definitely has lap number 1. Here's a blow-up of that. That's actually my daughter, Che Graham, age 7, and Paul is age, well, little omega. And the new discovery is the following. In 1994, there's Che Graham, age 32, and Polybachi, age omega to the omega. So there's a 2-cycle in this graph. And we don't know whether Paul has Erdős lap number 2 or Che has Erdős lap number -1. But anyway, it leads to some interesting questions. And with that, I leave you to go to lunch. Thank you.